Hello, this is Peter Welander. I'd like to welcome you to what I hope will be the first of a number of tutorial videos that we're going to be producing here at Control Engineering. I'd like to welcome you to the Control Engineering Test Kitchens, better known as my basement. One of the things that I've found in the work that I've done for Control Engineering is that it's hard to find something that gets as much involvement from readers as temperature sensors. Every time I've written something on the topic of thermocouples or RTDs or whatever, there's no shortage of customers and readers that will write back to me and say, that tell me that I've either said something good or I've said something bad or I've told something that's a simplification, and by golly, if their product can do exactly what I said really can't be done. So one of the first things that I thought I would deal with is the topic of thermocouples, because that's one that I think early on I said, that's one type of technology that you could produce by yourself if you had to, using things that you can buy at your typical hardware store. So one of the first things that I want to do is demonstrate the concept of a thermocouple using just literally some things that I found lying around here in the basement. Our first subject here is a thermocouple made with just some wire that I had some number 12 steel wire with some number 12 solid copper wire wrapped around it. This is just your everyday Radio Shack digital VOM, but one of the things that it does have that's very useful for us is a range that reads from 0 to 300 millivolts. And given that thermocouples put out very low voltages, we need something of that magnitude to be able to read the signals. So you can see that I've clipped two of the thermocouple wires there. The black one goes to the steel wire, the red one goes to the copper wire. I don't know if I've got the polarity right, but we'll see that in just a second. So what we need now is a source of heat. So I'm going to turn on my handy propane torch here. Lay it on the table where the flame is hitting the tip of the wire. So those two pieces of wire, take the heat away now and see what happens as it cools. So simply by heating those two pieces of wire, we created a voltage. And now as the wire is cooling, you can see it going down. It wasn't much of a voltage, it was just over about 1.5 millivolts, but it's a voltage nonetheless, and you'll see that the voltage goes down as the wire cools. A thermocouple takes advantage of the effect that every kind of wire, every kind of metal does not have the same Seebeck effect, so that different materials will create a different voltage for the same temperature gradient. Let's try a slightly more sophisticated setup using some actual thermocouple wire. The wires that are coming out of the crock pot, and you can see coming around the table and attached to the alligator clips, are actual Type T thermocouple wires. They were given to us by the nice folks at Moore Industries for this demonstration. There are two kinds of wire. The red wire is actually a copper-nickel alloy, and the blue wire is just plain copper. So what we've done is we've put this now into the pot, and you can see as the water warms up, you'll have to take my word for that, the water is warming up, that the voltage is increasing on the readout. It's up to 1.1 millivolt, now it's up to 1.2 millivolts as the water gets hotter. The voltage you see from a thermocouple is the voltage difference between the two different wires with their corresponding Seebeck coefficients. In other words, the two different alloy wires produce different voltages for the same temperature gradient. The larger the difference, the easier it is to measure. We call the point where the wires join a junction, and that is the point where the measurement is taken, even though the voltage is generated anywhere on the wire where there is a gradient. While this setup produces a voltage, all I can do is tell you the temperature differential between the hot and cold ends of the wires, not an actual temperature reading. To get a meaningful temperature measurement, you have to know the reading at one end or the other. We have to make one of the junctions a reference junction at a known temperature. So in order to get a thermocouple to be able to give you an absolute temperature reading, you have to be able to introduce a known temperature into the circuit somewhere. Now if you look at our little crock pot over here, you'll notice that there is in fact steam coming out of it because the water is getting very close to boiling. In fact, it's kind of is boiling now. Then you'll notice next to that there's a glass of ice water. Now notice that the red wire you can see here coming around there goes from the pot to the ice water. That's our copper nickel wire. The blue wire is this blue wire here is the copper wire, which goes to the alligator clip, and this white wire here is also copper wire, which goes to the other alligator clip. Then we're showing the reading on the VOM. We are up to 4 millivolts. With the water in the crock pot at a full boil, and the other end of the wire in the ice water. Now according to a type T thermocouple table, with the reference junction in the ice water and the boiling water at 212 degrees Fahrenheit, we should be getting a reading of exactly 4.253 millivolts. Given that we are at the absolute lowest end of this rather unsophisticated meter, the fact that we're at 4.0, I think we're doing really well. Now if we were to turn off the cooker, so let's leave this for a few minutes and come back and see what the voltage reading is. You can see it's already beginning to drop. Okay, so the water in our little crock pot has been cooling now for a little bit. So let's take a look and see what the voltage reading is now. So the water is beginning to cool off. You can see it's still steaming a bit. It's hotter than I'd want to stick my finger in, but it has cooled off somewhat. The voltage reading will continue to fall along with the temperature. According to the chart now at 2.4 millivolts, our temperature should be somewhere in the vicinity of about 130 to 140 degrees. So that feels about right. I don't really want to plunge my hand in there, but it's not going to scald me either. This works, but obviously it wouldn't be practical in an actual field installation to have a cup of ice water as your reference junction. So in a typical I/O situation or in a thermocouple transmitter, you're going to use some other temperature device to provide the reference temperature, typically a thermistor in most applications. So let's put this to a little more practical use, even though it's a slightly rainy Memorial Day. 3.2 millivolts. Looks like we're almost done here. For Control Engineering, this is Peter Wielander, Process Industries Editor. Thanks for watching.